Workbook Unit 1 M. This is the first exercise on projectile motion, and you can see here that this person throws a ball and it's thrown horizontally. So this initial velocity is horizontal, which means that the angle is 0. It's got an initial speed of v. From the top of a cliff, height h. So notice how I'm labeling all of these things. So if you're at height h initially, this is h initial, and your y position here at the end is 0. We don't know the final velocity at this point. We also do not know the angle, right? We don't know that. We don't know how much time it takes. We're going to assume that time starts at 0 up here. And we also are going to say, you know, what you're doing for all projectiles is you're saying, here's your coordinate system. So this x initial, right, we're at 0 here. And this x at the end, we also don't know, but this has a name. It's called the range. Okay, so this is, and this has a name. This is called hang time, the amount of time it's in the air. So you want to label all those things. And that's kind of what's going on in Part A. So these problems are just kinematics problems, and when you look at the information that you have, you know, I like to organize everything in a very systematic way, and I'm going to use the same techniques that I've used or been using for other kinematics problems, listing all the givens. Right? And we only have 5 in kinematics. We're looking for initial velocity, final velocity, acceleration, distance, and time, or displacement and time. So and I'm going to divide up the x and the y axis because the two axes are independent of each other. Now they're related, but they're independent. They're related through time. This has to be the same. The hang time for the ball is the hang time, whether you're talking with the x or the y axes. So when we talk about the initial x velocity, well, that was given because it's thrown on the x. So you would be like v, right? This is just v. And what you do is to find the x component, you generally multiply by cosine of the angle. But cosine of 0 is just 1. So we don't need to worry about it, right? Because it's just like v times 1 is v. So then v times sine of 0, well, sine of 0 is 0. So 0 times v is 0. So that's how I figure that out. Sorry, it's so squished. Final velocity, we don't know. Acceleration is a given for all vertical motion. So if we look at this ball, any projectile, we only have gravity acting on it. The force of gravity, it's written like this. If there's only that one force and there's no forces on the x, that means there's no acceleration on the x, and we have acceleration due to gravity on the y-axis. So this is a rule that is always given for projectiles or for free fall if you're only looking at the y-axis. X position, this is your range, your delta x here, or d sub x. This is what you don't know, right? We don't know the range, but the y we know is the change in the y position, which is final minus initial position. So it's going to be 0 minus h, which is negative h. So that's your y, and this we don't know. So what equation will help us find this time? Well, if you look at the x, you only have initial velocity, you have acceleration to 0, you don't know anything else. And we know from our kinematics, equations, we only have 3 equations. And if we have 3 equations, right, you have to have, right, each one has 4 different variables. So in other words, in order to use an equation, you need 3 out of the 4, so you could solve for the 4th. So if you only have 2, that's not going to be so helpful. Here we've got our initial velocity is 0, or acceleration. We've got this displacement that enables us to find time because we've got 3 out of the 4. So this is going to be the delta d equals VOT plus 1/2 AT squared. On your AP equation sheet, it's going to look like this. X equals X initial minus VO plus VOXT plus 1/2 AXT squared. I tend to use this shorthand. So we were going to rearrange this for time. So if we're doing the y-axis, it's going to be VOY times t plus 1/2 AY t squared. So we're going to use these values. This we know is 0. VOY is 0, so that makes this whole term drop out. This is negative h. This is 1/2. We've got negative g, we'll leave it as, or 9.8, you can say, times t squared. So this is going to be 2, right, because we're going to multiply both sides by 2h over g equals t squared. Therefore, t is going to be the square root of 2h over g. To find the horizontal distance, we're going to use we're going to use the same equation but for the x. So we're going to do delta x equals VOXT plus 1/2 AXT squared. Since acceleration is 0 on the x, this term drops out and we're left with dx equals v times t, which means that I've got, since we have an expression for t, you now have an equation v times the square root of 2h over g. How, if at all, would the equations written in C and E change if the projectile was thrown off the cliff at an angle above the horizontal? Well, now this is kind of interesting. So if we go back to these equations, we will have negative h equals v sine theta t. So this is our v from that, right? Plus 1/2 negative g t squared. So this is going to be, let's write this. So I'm just rearranging it, right? So let's simplify that just a little bit. 2h plus v sine t, sine theta times t over g. And then this is going to go into our dx equals VO cosine theta t, right? This term still drops out. So this is going to be dx VO cosine theta times this entire kind of messy thing. So if you have cosine of theta and sine of theta, and these are between where theta, right, is between 0 and 90. How does that affect it? Well, cosine of theta is going to be, and sine of theta will be between 0 and 1. So it's going to be a decimal. So that means that this value is going to go down here, right? And therefore this value, but this value is going to now, there's going to be something here. So this value goes up a little bit, but this value goes down. So this value increases a little, this value decreases, right? Because you're multiplying by a fraction, so this whole thing's going to go down. So when you go up in this direction, instead of just straight, you're going to spend more time in the air, right? So the time is going to increase, but your range will decrease. Sorry, not your range, but this value will decrease because you have less thrust this way, but because you have more time, you're probably going to end up going a little farther than you did, or as close to it, right? Either like this or like this. Depends on the actual value. Though when it's 45 degrees, it's going to, get to be it's going to get pretty big. But when it's not, when it's anything more or less, you're either going to spend more time in the air or you spend even less time in the air. So that it's going to be somewhat flexible in there. Now, if you're going to evaluate from the ground, the longest possible range is going to be given by theta equals 45 degrees. It's a little harder to decide what's going on when it's from a cliff.